Good morning, students. So, in this class, we are going to discuss the representation of angular momentum. So, which is a very important concept in quantum mechanics. In fact, we learned in the last class about angular momentum, which was represented by L. And of course, we learned the eigenvalues of L squared and Lz. We have given importance to these two quantities, L squared and Lz. And of course, we learnt about the ladder operators L plus L minus. Okay, and some commutation relations we learnt. But it is not enough to study the complete structure of angular momentum. So, the vector atom model, which says that the total angular momentum is the addition of linear angular momentum and spin angular momentum. Okay, it's very important one. Capital J equals capital L plus capital S. So this is what the vector atom model says. This is about spatial quantization. The space is quantized. The direction is quantized. When you are going to apply the magnetic field, the direction is quantized. So this is what we are going to learn today. So when we talk about capital J equals capital L plus capital S, which corresponds to small j equals small l plus small s. Small j stands for the total quantum number, so which is equal to orbital quantum number plus spin quantum number. Okay, so we have capital J equals capital L plus capital S. Similarly, small j equals small l plus s. So which is very important. This is the base in quantum mechanics. And certain experiments, especially spectra of alkali metals and anomalous Zeeman effect and Stern-Gerlach experiment, they prove that some additional angular momenta exists that involves half integral quantum numbers. And in the last class, we discussed about L. L was an integer, integral numbers starting from 0. So L goes from 0, 1, 2, 3, n minus 1. N stands for principal quantum number. Okay, so it says that this is integers, integral numbers. So L is an integral number. That means L equals 0, 1, 2, 3, n minus 1. Okay, if we want to find out the total values, angular momentum values, I have to use the formula 2L plus 1. Okay, so if we want to know the values, for example, if we are going to apply the magnetic field for the spectrum, so splitting of spectral lines in the presence of magnetic field is nothing but we know already about Zeeman effect. Okay, so the components are split. How many components are split? So we need to have the values which we use 2L plus 1. That formula will be using. Okay, suppose L equals 0. So you will have only one value. L equals 1. 2L plus 1. You substitute L equal to 1. Then you will get 3 components. L equal to 2. You will get 5 components. So in that way, how many components can be split in the presence of magnetic field? So we can come to know 2L plus 1 using this formula. But certain experiments like spectra of alkali metals. So alkali metals, usually potassium, sodium, and they show that fine structure of spectra. They show. For example, if you view the spectra with the help of high resolution power of using any spectrometer, we will have a dense of lines, overlapping of lines. What we call this as fine structure spectra. And that spectra shows that some additional angular momenta exists, which shows that half integral quantum numbers. Especially after the invention of the spin in the year 1922 by Stern-Gerlach experiment. So split of lines when silver atom passes through the non-uniform magnetic field, there will be 2 spots. One is plus and minus 1, up and down, spin up and spin down. So that was the origin for the spin concept. So after that, after 4 years in the year 1926, it was put forth by Uhlenbeck and Goldsmith about vector auto model and spatial quantization. And in fact, Zeeman effect says that the spectral lines which are split into components, odd number of components. Suppose if there exists even number of components by taking certain other elements, even number of components, then what we call this as abnormal Zeeman effect or anomalous Zeeman effect. So there will be even numbers. So as I said earlier, 2L plus 1, if L equals 0, L equals 1, L equals 2, you will get odd number of components, splitting of odd number of components. Okay, you have 1, 3, 5, 7 goes on. But if you have even number of components in abnormal Zeeman effect, so we'll have to go only with L as an integral, half integral numbers. I repeat, come on, it's very simple idea. You have L is an integer numbers. Okay, L is an integer numbers. If you substitute to get the total values, total components of splitting, you will have to use 2L plus 1, that formula. For L equals 0, L equal to 1, L equal to 2, you will get only odd numbers. Okay, but later, after the discovery of Zeeman effect, normal Zeeman effect, Thomas Perrin from Ireland, he found out using some other elements, he found out even number of splitting. Suppose use the same formula, 2L plus 1. Use the same formula. You will get only odd numbers. To get even numbers, L must be 2L plus 1. That L must be half integers. You just go with the formula 2L plus 1. 2 multiplied by 1 by 2 plus 1. You will get 2. 2 multiplied by 3 by 2. You will get 4. See, even number of splitting here. Thomas Perrin found out, but he didn't explain. He couldn't explain. At the time, spin was not found out. Okay. Later, after 1926, only the explanation was correct. Explanation was given. So now we talk about even number of splitting. What we call this as abnormal Zeeman effect, anomalous Zeeman effect. So one is even number, another one is odd number. Okay. So in order to find out the even number, L must be half integrals, correct? But L is already integers. So we'll have to add L with some other half integrals. Only then we will get the total angular momentum. So that's why they put forth this idea of J equals L plus S. Okay, so J stands for total angular momentum. L stands for orbital angular momentum, which goes with integral integers. Okay, integral numbers. And S is half integer numbers. Put together you will get half integer plus integral numbers. Integer as well half integers. Now this will satisfy. Okay, so we call this as capital J, which is nothing but total angular momentum. So as I said, the integral values of L will be exactly like 0, 1, 2, 3. Half integral value of S will be S plus or minus half. You add these two, so that will give you J. J will contain both integers as well half integers, which will satisfy the total value is nothing but 2J plus 1. So earlier we said 2L plus 1. Now we are going to say as 2J plus 1. Okay, so that's the idea. So we are going to have the commutation relations for J. So whatever the commutation relations that we studied for L will be applicable for J also. Okay, J also. The possible half integral results follow directly from the commutation relations from angular momentum components. Okay, so this is the idea. As I said, 2L plus 1. Now we are going to study 2J plus 1. J stands for L plus S. Okay. So capital J equals capital L plus capital S. Total angular momentum, orbital angular momentum, spin angular momentum. So whenever we talk about spin, for example, electron which revolves around the nucleus, so charged particle orbiting, so it has to have orbital angular momentum. Okay, it has to have orbital angular momentum. And spin is an intrinsic property, intrinsic angular momentum. So we'll have to add these two. So we'll get a total angular momentum. Whatever the rules that we have followed for L, the same rule also is applicable for J, the commutation rules. The components also, so not only the main one, the components also will obey the rule. So Jx equals Lx plus Sx, Jy equals Ly plus Sy, and Jz equals Lz plus Kzz. Okay, the same commutation rules for angular momentum they also. Okay. So this is the commutation rules for Jx. We learnt about Lx earlier in the last class. The same thing, Jx comma Jy with the commutation rule that will give you IH cross Jz with the permutation rule which I said earlier. Okay, so Jy comma Jz commutation will give you IH cross Jx. The commutation of Jz Jx will give you IH cross Jy. So all positive quantities. Okay, if you are going to take xy, you will get Lz. So xy you will get Lz there. So here also Jz. And what are the components? The components themselves will commute with each other. Okay, they will commute with each other. They will not commute. They will commute with each other. Okay, so we can measure simultaneously two components. So components themselves will commute. And the components of J and the operators are. So we are going to learn four things. One is J squared. Another one is ladder operator. So we learnt about L plus and L minus in the earlier class. So this is J plus. J plus equals Jx plus Ijy, and complex conjugate of J plus will be J minus. So which is nothing but Jx minus Ijy. Okay. So third one. The fourth one will be opposed Jz. Jx and Jy already they are included in J plus and J minus. Okay. So we know already that see here J squared, J plus, Jx, Jy and J minus and Jz. But Jx and Jy already included in J plus and J minus. Okay, so now we are going to concentrate only on four things. One is J square, J plus, J minus and Jz. Our aim is to find out two concepts. One is the eigenvalues and corresponding matrix elements. That's all. Okay, so we are going to find out the eigenvalues of J square, eigenvalues of J plus, eigenvalues of J minus and eigenvalues of Jz. One. And second one will be matrix elements. So we are going to find out the matrix elements of J square, J plus, J minus and Jz. Only two things we are going to find out in this class. So they obey all commutation relations derived for all operators like L, L plus, L minus. What are the commutation rules for L plus, L minus, L squared, Lz? The same rule will be applicable for J. Okay, same thing. Now, as we said about in the introduction, direction is changing. Okay, direction is quantized. So this is about vector auto model. Vector auto model in which you are going to apply the magnetic field in this direction. Okay, so you have an atom, you are going to apply the magnetic field in the z direction, Okay, the electrons which revolve around the nucleus will process now. It will process. Suppose if we consider the position of the electron is somewhere here. Okay, so this will process like this. And this J will give you the magnitude. This J will give you magnitude. And as I said, the projection of this will fall exactly on this axis. Okay, so your mh bar will be the direction. Suppose your electron is here, you are going to project it. So your J will be here and the projection exactly somewhere here. Okay, so that will be your mj. Suppose your electron is here somewhere, so projection will be somewhere here. Okay, and this will be your mj. This is your magnitude. Magnitude will be always constant. See, magnitude is constant. Here magnitude is constant. What of the direction? Direction alone changes. Okay, direction. So this is quantized. We are going to use only discrete basis. Okay, discrete. Here the direction is quantized. Your magnitude will be h bar root of j into j plus 1. That is your magnitude. Your direction will be your mh bar. Okay, so this is z component. So this is exactly something like this. You have a simple pendulum. Okay, you have a simple pendulum. We explained earlier. So you have a simple pendulum and we have a conical pendulum. Suppose if we fix simple pendulum somewhere here, and you are going to add the conical pendulum now. Put together, we call this as spherical pendulum. Okay, we call this as spherical pendulum. So we consider only the vector automodel exactly in this model. Okay, the electron which revolves around the nucleus with a spherical pendulum, like exactly spherical pendulum. Okay. Okay, so this is about the length and this is about the direction. So as I said, we are going to learn two things. One is the eigenvalues, another one is matrix elements of j square, j z, j plus and j minus. That's all. Okay, so all the four things. The first thing we are going to concentrate only on j z, which will be very easier. If you know the techniques for finding out the eigenvalues and matrix elements of j z, that will be easier for other things. Okay, so we are going to concentrate only on j z first. So before that, the square of the angular momentum j squared commutes with components. The square of the angular momentum will commute with its own components. See here, j squared comma j z with the commutator will be equal to 0. So they will commute with each other. Simultaneously you can measure both the quantities. It means one. Second one, they will have simultaneous eigenstates. Suppose if two operators they commute a and b, answer is 0. Okay, commutator a comma b equals 0. It implies that both will have common eigenstates. Both will have common state vectors. Okay, that you have to remember. Now, what are the components themselves? Jx comma jy. So they will not commute. See, jx comma jy will give you Eigen cross jz and other things. They don't commute. The square of the angular momentum j squared commutes with components and jx and jy, jz, but the components themselves will not commute. Components themselves will not commute. Okay, first point. Then second point will be j squared and jz, they commute with each other and it will have common eigenstates, simultaneous eigenstates. These eigenstates, the first time you are going to learn with eigenstate kept j comma m. So earlier we learnt about phi, ket phi, ket psi, ket chi. Okay, single state vector, correct? Or eigenstate, single one. Now we have inserted two things, j comma m. Both are bases. Like psi, chi, phi, same state vectors. They are also state vectors. J comma m, eigenkets. And two things are there. Okay, you should remember two are there. Okay, two basis states are there. J comma m. Okay. So they will have common eigenstates. So j comma. So the eigenstate for j squared will be j comma m. The same eigenstate will be for j z. So it implies they will have common eigenstates. So total angular momentum j and its components obey all commutations derived for orbital angular momentum L, we know already. So as I said, j comma m is nothing but common eigenstates. What we call this is called joint eigenstates. Okay, and of course they are all discrete bases. Bases are discrete and they will have a complete orthonormal set of states. Okay, suppose we want to find out the matrix elements. So matrix elements, the representation matrix elements is given by this expression, correct? So A is sandwiched between ket jm and bra j dash m dash. Okay, so this is your matrix elements. So our aim is to find out the eigenvalues and the matrix elements. Okay, our aim is to find out eigenvalues and the matrix elements. So that's all. So instead of A, you substitute j square, j z, j plus, j minus. That's all. Okay, we are going to get the matrices now. As I said, j squared and j z. Okay, j squared and j z will have diagonal elements. So very important one. We will have diagonal elements. We are going to look into now. We will see. So j comma m simultaneous eigenvectors for j squared and j z because they will commute with each other. So j squared acts on j comma m will give you eigenvalues j plus 1 h bar squared j m. Similarly j z simultaneous eigenstates. Okay, J is at acts on ket J comma M will give you eigenvalue M h bar J comma M, and J will have the values 0, 1 by 2, 1, 3 by 2. It's very important one. See, of course, we know the principal quantum number n goes with 1, 2, 3. Orbital quantum number goes with integers. Okay, integral numbers 0, 1, 2, 3 dot 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 n minus 1. Your J will be you add these two, L plus S equals plus or minus 1 by 2 for the electrons. Okay, you add these two, that will give you your half integral plus integral numbers. So this is a very important concept. Okay, so J goes from 0, 1 by 2, 1, 3 by 2 goes on, and of course M equals minus J to plus J. So M goes from minus J to plus J. So maximum value, and this will be a minimum value. Okay, so almost we have covered. So we discussed already L squared equals L into L plus 1 h bar squared. Similarly, J squared equals J into J plus 1 h bar squared. We know about L is that equals M h bar. Already we studied. So J is that equals M h bar. That's all. Is it okay? Now just multiply equation 5.30. Okay, 5.30 and 5.31. 5.30 we will multiply with J dash M dash. Okay, just take the bra of this one, bra of J comma M, and use the operation. So we will get this equation, correct? Just take bra of J comma M. So J dash M dash. When you are going to take the bra, immediately this will become indices J dash M dash. Already we have seen earlier. So J dash M dash J square J comma M. So J square sandwiched between Jm and J dash M. Okay, ket Jm and bra J dash M dash. So that will give you this value. Okay, and this is a number, eigenvalue. I can pull it out. So using Kronecker delta, this will become 1 if J equals J dash, M equals M dash. The answer will be 1. So you will get exactly like this. So this will be eigenvalue of J square. What about your J is that? J is that, as I said, take the bra of J comma M and use the operation, you will get the matrix element of J is that. So J is that sandwiched between your bra J comma M and get J dash M dash will give you this. Again MH will be eigenvalue. It's a number. You pull it out. And if J equals J dash, M equals M dash, this will become 1. You will get the eigenvalue. So eigenvalue of J is that will be M h bar, and eigenvalue of J squared will be J into J plus 1 h bar squared. Is it okay? So both will have diagonal elements. Okay, you should remember both will have diagonal elements. I'll say simply. See, for example, here we are talking about ket and bra. Okay, ket is a column vector or a row vector? Column vector. Bra, it's a row vector. Okay, now if J equals J dash, M equals M dash. In a matrix, suppose if we go for 3 by 3 matrix. Okay, if both the elements are equal. Okay, if both the elements are equal. Suppose in a matrix, we have 1, 1, 1, 2, 1, 3. You have 1, 1, 2, 1, 2, 3. Suppose if it is like this. If both the elements are equal, then those elements are called diagonal elements. Correct? 1, 1, 2, 2, 3, 3. They are all diagonal elements. Correct? And you substitute here as J equals J dash, M equals M dash. Both the elements are equal. Correct? You will get only diagonal elements. Okay? For J squared and J z, the answer always will be the diagonal elements. All because of this rule. Is it okay? So you will have only diagonal elements. So we have to use Kronecker delta function, and we have used Kronecker delta function. If J equals J dash and M equals M dash, you will get answer as 1. If it is not equal to 0, answer as 0. So half diagonal elements will be 0. Half diagonal elements will be 0. See, J is not equal to J dash, M is not equal to M dash. Okay, if they are equal, as I said, 1 equals 1, 2 equals 2, 3 equals 3, 4 equals 4, goes on for diagonal elements. So answer will be 1. Answer exists. Okay, if they are not equal for half diagonal elements, lower half diagonal elements or upper diagonal elements, that will be 0. Is it okay? Now substituting equation 5.34, 5.34 in 5.32, okay, we will have. Now we are going to substitute now. So we have j squared, this will be your, we are going to substitute this one in 5.32. So this is 5.34, this is 5.32, you substitute here. So instead of j dash m dash, j comma m, you substitute this one. So this is the complete expression for matrix elements of j squared. This is the complete expression for matrix elements of j z. That's it. So this is the expectation value of j squared, the expectation value of j z. So it's a matrix element in a matrix. Okay? Is it okay? The presence of the factors del j comma j dash and del m dash indicate that the matrices are diagonals. If j equals j dash, if m equals m dash, we have only diagonal elements, no other elements will exist. Okay? So thus the operator j squared j z will give you only diagonal elements. Very, very important concept. Okay? Now we will solve it. As I said, we will solve some problems. First we will take j z. It will be easier for you. J z. So we are going to find, we know already the eigenvalue of j z will be m h bar. We know already this one. So first we will take the case j equal to 0. If j equal to 0, m equals, what is the expression for m? If j equal to 0, that will goes from minus j to plus j. Okay. So m will be 0. You will have to find out the total number of values for the matrix. How many matrix elements exist? We will have to use this formula, dimension formula, d equals 2j plus 1. So j equals 0 means you will have only one element exists in a matrix. That is 1 by 1 matrix. That element will be 0 because m equals 0. You substitute m equals 0, you will get j z equals 0. Eigenvalue is 0, correct? Only one element exists. So that element is nothing but in a matrix 0. Is it okay? 0 is the value of j z for j equals 0. If j equal to 0, m equals j equals 0, m equals 0 because m goes from minus j to plus j. J equal to 0. So m will be 0. If m is 0, j z will be 0. But we have only dimension of a matrix is nothing but only one element exists in a matrix. Is it okay? So you will have j z equals 0. Now you go for j equals 1 by 2. The next value. If j equal to 1 by 2, your m will be minus j to plus j. So minus 1 by 2 to 1 by 2. Is it okay? So we have two values now. What is the dimension? Dimension of the matrix 2j plus 1. So 2 multiplied by 1 by 2 plus 1. That will give you 2. So there exists two elements in a matrix. Two elements. Two elements means you have 2 by 2. 2 by 2. Sorry. 2 by 2 matrix. Correct? So 2 by 2 matrix. So now we must have 4 elements. Correct? We must have 4 elements. Out of 4 elements, the diagonal elements alone will exist. Half diagonal elements will be 0. So these two will be 0. First point. And second point will be for m equals 1 by 2. You substitute here. M equals 1 by 2. So you will get j z will be h bar by 2. The first value. M equals minus 1 by 2. Your j z will be minus h bar by 2. So those two elements are diagonal elements. We learnt already earlier. So your j z will be, you pull h bar out, that will give you 1 by 2, 0, 0, minus 1 by 2. Is it okay? Only diagonal elements alone exist. Okay? Is it okay? Now we will go for the next case. J equals 1. So if j equals 1, your m will be minus j to plus j. Minus j to plus j. So minus 1, 0, 1. Here we have inserted 0 here. Here we have not inserted 0 here. You have to find out the difference. You didn't ask me this question. Here there is no 0 here. There exists 0 here. Why? What is the reason? Because it's an integer. This is half integer. Half integer. Okay? So that's why you have inserted 0. Is it okay? You didn't ask me this question, but it's very important. Minus 1, 0, 1. So now there are 3 values. So you'll have to substitute 2j plus 1 for total number of values to find out. So 2 multiplied by 1 will give plus 1, that will give you 3. So we'll have to have 9 components, 3 by 3 matrix. Correct? 9 components, 3 by 3 matrix. In a matrix you'll have to have 3 by 3, 3 column and 3 rows. So for m equals 1, Jz will be, your Jz will be, formula will be m h bar, your Jz will be h bar. For m equals 0, Jz will be 0. M equals minus 1, Jz will be minus 1. So in a matrix, Jz will be h bar, you pull h bar out, 1, 0, minus 1. So they are all diagonal elements. Off diagonal elements will be 0. Is it okay? How to represent Jz as matrix? So we have found out the eigenvalue of Jz and matrix element of Jz. Very simple one. Is it okay? Now, okay. So now we are going to have representation of matrix element, complete representation of matrix element. And of course, we know the eigenvalue equation of this. Okay, we know this one, eigenvalue equation, and matrix element is given by this. We'll have to use Kronecker delta function as given in the slide. Okay, now very simple one. Come on. As we said that for j equals 1, we are going to have 3 by 3 matrix. Okay, so this will be your 3 by 3 matrix. And what of this one? You will have j comma m is represented in terms of 1 comma 1, 1 comma 0, 1 comma minus 1. So this represents, the first one represents j, second one represents m, the first one represents j, second one represents the second value of m, third one represents j, and this one represents the third value of m. So you have 1, 0, minus 1. Okay, this is for the ket vector. And similarly, you can go for the bra vector. See here, bra vector. Okay, the first idea. The second idea is you just have these two. This is 1 by 1, 1 comma 1, and this will be also 1, 1. Okay, ket 1, 1, bra 1, 1. So which falls on this first category, first diagonal elements. Go for the next one. We'll have 1, 0. 1, 0. Here we have 1 minus 1, 1 minus 1. So all the diagonal elements alone will exist. Okay, according to Kronecker delta function. Okay, if j equals j dash, here m equals m dash. See here, of course, in all the things j equals j dash, it's okay. But here m equals m dash, here m equals m dash. So it exists. Only diagonal elements alone will exist. What is the other one? You just take this, in this case, m is not equal to m dash. M is not equal to m dash. So answer is 0. Okay, upper diagonal elements will be 0. Similarly, lower diagonal elements also will be 0. Only diagonal elements alone will exist. Is it okay? Now you can pull h bar out. You will get the complete matrix element of Jz. And this is the matrix representation of Jz. Okay, so J is a sandwich between ket 1, 1, bra 1, 1. See, ket 1, 0, bra 1, 0, ket 1 minus 1, bra 1 minus 1. So they are all diagonal elements. Half diagonal elements can be written using this one exactly like this. So the first one represents J, the second one represents M. Okay. So this is the complete representation, general representation of Jz in terms of matrix. Any doubt? Okay. So whatever we have learned for j equal to 0, j equals 1 by 2, j equals 1. Okay, and j equals 3 by 2. So we are going to put together in a table, and in fact you can see this h bar can be pulled out this side. So j is by h bar, correct? You can take this h bar out. Similarly for all the other 2 by 2, 3 by 3, 4 by 4 matrix also we can pull it out. So I have written j is by h bar, first point. Okay, so j is by h bar. This is a matrix table for j is using this formula. So using this eigen value equation, so we have already used this one. Okay, and also matrix element. Now just see here, j comma m I have written here. So this stands for, all the value stands for j. This stands for m, corresponding j. So j equal to 0, you have m equal to 0. J equal to 1 by 2, m will be minus 1 by 2 and 1 by 2, correct? So 1 by 2 here, j equal to 1 by 2 minus 1 by 2. For j equal to 1, the value will be minus 1, 0, plus 1. So 1, 0, minus 1. 3 values. For j equal to 3 by 2, you will have 4 values, correct? Here there exists 0. Don't forget, there is no 0 here. So you have to remember, okay? There exists 0 here. Okay, integer, full integers, half integers. Similarly, you can go for the this side also, j dash, m dash, where m dash will be 0, j dash will be 0, m dash will be 0. J dash will be 1 by 2 and your m dash will be 1 by 2 minus 1 by 2. Your j dash will be 1 and your m dash will be 1, 0, minus 1. So something like that. Now the first element which we calculated, can you remember? 2j plus 1 for j equal to 0. So we obtain only 0. Okay, matrix element only one element. So we have written 1 here. For the next one, j equal to 1 by 2, we obtained this one, 1 by 2, 0, minus 1 by 2. For j equal to 1, we obtained this one. Okay. Similarly, for j equals 3 by 2, use 2j plus 1, 3 by 2. We'll have 4 by 4 matrix, correct? J equals 3 by 2, use 2j plus 1, 2 multiplied by 3 by 2, so 3 plus 1, that will give you 4. So 4 by 4 matrix. Okay, any doubt? And of course, j is a sandwich between 1 by 2, just take this case. 1 by 2, get, that will give you h bar by 2. This is for h bar by 2. We have pulled h bar by 2 this side, from right hand to left hand side. So that's why it is there as 1 by 2. Okay, so similarly for minus h bar by 2, minus h bar by 2. So this is the way to represent the general representation of matrices for J. Any doubt? Now we'll go for the next one, J squared. So if you are so thorough with the first one, J, it will be very, very easier for you to calculate for the eigenvalues and matrix elements for rest of the terms, J squared, J plus, J minus, and of course Jx and Jy, they are included in J plus and J minus. Okay, so now the eigenvalues of J squared will be J into J plus 1 h bar squared, does not depend on m. Okay, look at the expression, does not depend on m, only J alone, very easy. So if J equal to 0, what is the answer? J squared will be, come on, J equal to 0 will be h bar squared. Is it so? Is it correct? J equals 0, the answer will be, answer will be 0. Come on, you substitute here. Okay, so we have only one matrix element, the matrix element is 0. Okay, J equal to 0, answer will be 0. If J equal to 1 by 2, don't bother about m because it does not depend on m. Okay, here we have written to complete the theory, that's all. So J equal to 1 by 2, so 1 by 2 multiplied by 1 by 2 plus 1 multiplied by h bar squared. Okay, so that will give you, come on, so you will have 3 by 4 h bar squared, correct? 1 by 2 plus 1, that will be 3 by 2. 3 by 2 multiplied by 1 by 2 will give you 3 by 4. So 3 by 4 h bar squared, the value will be 3 by 4 h bar squared. What are the dimension? 2j plus 1, your j will be 1 by 2. So you will have dimension will be 2. So 2 by 2 matrix, 2 rows and 2 columns. So that will be 4 elements. Okay, of course, half diagonal will be 0 as we have done earlier for J z. Okay, and you have J squared will be h bar squared 3 by 4 for J equals 1 by 2, correct? And 3 by 4, this also for J equals 1 by 2. Is it okay? And how to represent in terms of matrices. So this is the eigenvalue equation for J squared as well for the matrix elements. So matrix elements for the J squared matrix elements. So J into J plus 1 h bar squared with a delta function. And the value will be, for example, we just take J equals 1. Okay, next case. j equals 1 means 2j plus 1, so we'll have 3 by 3 matrix. So we'll have 3 by 3 matrix. Okay, we are going to have the value j equals 1. So j equals 1 means j squared will be 1 multiplied by 1 plus 1, that will give you 2 h bar square. Okay, 2 h bar square. Just as I said earlier, this will be your j comma m, this will be your j dash m dash. Only diagonal elements alone will exist. For j equals j dash, m equals m dash. So only diagonal elements will exist. 2 h bar square, 2 h bar square, 2 h bar square. Is it okay? So all the other upper and lower diagonals will be 0. The complete matrix element matrix representation will be j square sandwiched between ket 1 1 and bra 1 1. Okay, and these things will represent the diagonal elements. Okay, so those will be off diagonal elements as we have seen earlier. And j squared will be, you pull 2 h bar squared out, that will give you 1 0 0 0 1 0 0 0 1. Only diagonal elements will be with this. So very important thing, for j squared and j z, only diagonal elements, all because of this factor, j equals j dash and m equals m dash, both are equal. Okay, if you put the condition as j equals j dash, answer will be 1, and m equals m dash, answer will be 1. Is it okay? Very simple one. So now we'll go for j squared. So j squared by h bar squared. So that's a printing mistake here. This is for j squared. Okay, this is for j squared. So j squared by h bar squared. Here h bar squared is there, correct? You pull this h bar squared down this side. So you will have j squared by h bar squared. You can have a complete matrices for all the 4 things. J equals 0, j equals 1 by 2, j equals 1, j equals 3 by 2. Okay, as usual, the same argument. For j equals 0, m will be 0, of course we know already. For j equal to 0, you substitute here, you will get 0, so 0, 1 by 1 matrix. For j equal to 1 by 2, so you substitute here, you will get 3 by 4, 3 by 4, 0, 3 by 4. Similarly, for j equals 1, you will have 1 plus 1, 2, so that will give you 2, 2, 2. Of course, you have 2 h bar square. H bar square we have already pulled out this side, to left hand side. So that's why it is j squared by h bar square. The table goes. Similarly, for j equals 3 by 2, you will have 15 by 4. 15 by 4 goes on. Only diagonal elements alone will exist. And for j squared, this is for j squared. Okay, j squared sandwiched between ket 1 by 2, 1 by 2 with bra 1 by 2, 1 by 2 will give you that value. Okay, 3 by 4 h bar square. 3 by 4 h bar square. So this is j squared. It is not j, is a j squared. Okay, any doubt? Now the complete expressions, total, put together, generally we can write this as, for this is for j squared and this is for j z. J squared will be h bar squared, j plus 1, j plus 1, only diagonal elements alone will exist. Off diagonal elements will be 0. And for j z will be, it goes from minus j to plus j. Okay, so j minus 1, j minus 2, dot dot dot, minus j. Off diagonal elements will be equal to 0. Okay, and m goes from minus j to plus j, dimension will be 2j plus 1. So 2j plus 1 rows and 2j plus 1 columns. Only diagonal elements will exist. Okay, any doubt? So we have finished only for the part, that is j squared and j z we have finished.